Hello, Algebra 2 students. This is a lecture. We're kind of introducing the chapter on probability, and this is going to be specifically focusing on the number of ways that we can accomplish a given task. There are going to be four different methods that we're going to use in section 10.1. The first of which is called the fundamental counting principle. The fundamental counting principle states that if one event can occur in a given number of ways, and another event can occur in another given number of ways, then the number of ways that both events occur is just going to be what you get when you multiply the two given number of ways. So if one event can occur in 10 ways and another event can occur in 5 ways, and you want to know how many ways can both events occur, that would be 50 ways. You just multiply it. We have another method for counting things, and that's going to be using factorial. And this states specifically about order. If we have n objects or items, and we want to select all n of them and order them, okay, order is important. So if I just switch two things, it creates a different order. The notation for this task, if you want to accomplish this, is just going to be n factorial. If you want to organize n objects, you're going to do n factorial to calculate that. And what n factorial states is you just take the number and you multiply that by 1 less than the number, and then you multiply that by 2 less than the number, and you keep doing this task all the way down to 1. There is a button for factorial in your calculator. If you want to figure out 5 factorial, you would type in 5 first, and then you'd go under math, and then a lot of the stuff we're going to be doing in this chapter, because it's our chapter on probability, you push math and then slide over to prob, and you'll see the exclamation point is the fourth one down. So 5 factorial is 120. How do we do that? Well, that's taking 5 times 4 times 3 times 2 times 1. If you do 5 times 4 times 3 times 2 times 1, guess what? You get 120. So once again, factorial is if you have n objects, if you have 5 objects, and you want to figure out how many ways that you can organize all 5 objects. Okay, if you had 5 of some trinket out in front of you, and you were like, how many ways can I organize these 5 objects in a way that you can kind of differentiate between them? That would be 5 factorial. Permutations, on the other hand, should be a review word for you, and it is the number of ways that you can select R out of n objects. So let's say there are 10 objects, and you want to know how many ways that you can select 3 of them. Okay, you're not taking all 10 in this case. If you had 10 objects and you wanted to organize all 10 in which order is important, that would be factorial. But if you had 10 objects and you only wanted to figure out how many ways that you could select 3 of those objects, that's called permutations. And NPR, basically what it would look like, let's say you had 10 objects and you wanted to select 3 of them using permutations. This is how it would look. 10P, big P, 3. P is for permutations. The first number is how many you are selecting out of, and the second number is how many you are selecting. If you wanted to do that, you would take n factorial, which would be 10 factorial, and divide that by subtract them factorial. 7 factorial, right? Because 10 minus 3 is 7. 10 factorial divided by 3 factorial, I could type that into my calculator, but it's also worth noting that there is a permutations button, once again, under probability. You just go over to prob, you'll see NPR right there, and you're going to select that. So 10, I type that in first, P, and then now I'm going to type in 3 here. 10P3 is 720. So what you did there is you just type, well, yeah, it's effectively 10 factorial means 10 times 9 times 8 times 7 times 6 times forever, right? So I could also write it as 10 times 9 times 8 times 7 factorial, because 7 factorial means 7 times 6 times 5 all the way down to 1. And I'm dividing that by 7 factorial. This is how I was originally shown how to do this. So 7 factorial divided by 7 factorial, they cancel, and you just have 10 times 9 times 8, which is 720. Now, for your guys' use of this, you're probably not going to have to do that at all. You'll just be able to go 10 and select permutations and then go over to 3. The fourth and final counting principal property type thing that we're going to be using is permutations with repetition. This will also be referred to as distinguishable permutations. And an example of this would be saying how many ways can I write distinguishable permutations of the letters in the word Miami. And so essentially what makes this different is if we are figuring out how many ways we can organize the letters in the word Miami, if I switch the I and the I haven't made a different word. That's the exact same word if I just switch two letters that are not distinguishable between them. And so that is the scenario in which you would use distinguishable permutations or permutations with repetition. There are some objects, like the letter I here, that's repeated. And if that's the case, let's say that I want to know how many ways could I write the word Miami. N factorial is the numerator, and that's the total number of letters in the word. So there's 5 letters in the word Miami. So that would be 5 factorial, and divided by this S1 factorial times S2 factorial. What that's stating is for every repeated letter, the number of times it's repeated factorial. So in the word Miami, M is repeated twice. There's an M here and an M here. So 2 factorial goes in the denominator. And also, I is repeated twice. And so another 2 factorial goes in the denominator. So if I were trying to figure out how many ways I could write the letters in the word Miami, where some objects are repeated, like M and I are repeated, this is the formula for doing that task. And I could go over to my calculator and do, I'm going to type in parentheses here, be really careful, math, and then PRB, select factorial, and then divide that by 2 factorial. Now I know what 2 factorial is. I know that 2 factorial is just 1. But for the sake of this, I want to show you how you type it in. 2 factorial times 2, then go back over to factorial again. That's how I'd want that typed in. 5 factorial divided by 2 factorial times 2 factorial. I can push enter, and I find out that there are 30 ways that we could organize the letters in the word Miami. Let's do the same thing for Tallahassee, just for fun. This would be a good one for you to pause to try it out. In total, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters in the word Tallahassee. And then we're just going to go for every repeated letter, the number of times it's repeated, factorial, goes in the denominator. So A is repeated 3 times. 1, 2, 3. So there's a 3 factorial down here. L is repeated twice. So there's a 2 factorial down here. S is repeated twice, another 2 factorial. And then we can say E is repeated twice. That's another 2 factorial. So 11 factorial divided by 3 factorial times 2 factorial times 2 factorial times 2 factorial. Be very careful with how you type this in. 11 factorial divided by, you cannot just multiply all these things and say that factorial. That would not be mathematically sound. So we actually do have to think of these or go ahead and type it in. So I know 3 factorial. I know that 2 factorial is just 2. You guys should process that with me. Remember, 2 factorial just means 2 times 1. So I'm just going to do times 2 times 2 times 2. But if you did times 2 factorial times 2 factorial times 2 factorial, that would also give you the same answer. And what do we get? A lot. Factorial grows insanely fast. And we saw 5 factorial was 120. And it doesn't take very long to cause your calculator to go into scientific notation. I don't know if 10 will. But 10 factorial is, 3 million already. It does not take long for factorials to be getting to very large numbers. So there's our answer here. 831,600 ways that we could reorganize the letters in the word Tallahassee. And the reason it's not just 11 factorial, if it was just how many ways can we order 11 objects, that would just be 11 factorial. 11 times 10 times 9 times all the way down to 1. But the reason this is different is because if we switch these 2 letters, these 2 E's, if we switch the order, we haven't actually made something different. And so that would be not distinguishable between them. And so that's how we know to trigger this formula. So let's look at some examples. Here's an example. We have a sporting good that offers 3 different types of snowboards, 2 different types of boots. How many ways can we like make a set, a snowboard set? And so this is textbook fundamental counting principle. There are 2 different events occurring. In one event, selection of snowboard can occur in 3 ways. In the other event, selection of the boots can occur in 2 ways. And so in that scenario, you just take the 2 numbers and you multiply them and you get 6. Okay, one event can occur in 3 ways, one event can occur in 2 ways. Multiply them, you get 6. That's fundamental counting principle. This is, of course, going to be a distinguishable permutations problem. I like this example because we can actually kind of think of all the different ways that we can arrange this word. So let's say we didn't know the formula, and we just have the word peep, and we want to know how many ways that we can arrange it. I can just say, hey, peep is one of them, right? We have peep. We have, I guess, P, P, E, E. What else do we have? We have so PPEE, we have Pepe, PP, something like that. PEPE. You guys with me? That would be the only ways that we can start with the letter P, but then we could also start with the letter E. We could go EE, P, P, or we could go E, P, E, P, Ep, Ep, or we could go Epi. Isn't this fun? So I believe that's the only ways that we could reorganize these letters, assuming that you can't distinguish between these 2 E's, but you can't. Let's see if our formula backs that up. So the formula would say 4 factorial on your numerator, because that's the total number of letters, and then 2 factorial times 2 factorial. The reason why you'd have both of those 2's is because there's 2 letter P's and there's 2 letter E's. 4 factorial is 24. 4 times 3 is 12. Times 2 is 24. Times 1 is still 24. 24 divided by 2 factorial is 2. Times 2 factorial is still 2. So 2 times 2 is 4. And we get 24 divided by 4 is 6. So there's 6 ways, and that's what we got. I just kind of want to show you guys that the formula does work. I think that's kind of a good way to look at how we can reorganize things with distinguishable permutations. There will absolutely be some license plate problems on your quiz. I think the first 2 questions on your quiz are actually license plate problems. So this says that the standard configuration for a Texas license plate goes 1 letter, followed by 2 digits, followed by 3 letters. Assuming that letters and numbers can be repeated, how many possible license plates could be created? This is actually looking at our 4 options. We have permutations with repetition, fundamental counting principle, and then factorial. This is a fundamental counting principle problem. When we think about the license plate, here I'm going to actually just draw one. It's going to go letter. We'll just use red L for letter. And then it will go 2 digits. So it will go number, and then 3 letters again. Letter, 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 letter. And how this is a fundamental counting principle problem is you'll think of every digit or every character as an event. And so it starts out with a letter. Letters can occur, of course, in 26 different ways. So you take 26, and that's the first event. And the fundamental counting principle says just multiply that by the number of ways that the next event can occur. And the next event is going to be a digit. There's actually 10 digits if you count them, 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's actually 10 different digits. And so if the number of if the license plate has to go letter and then number, it would look like 26 times 10. Because the problem says that digits and letters can be repeated, the next one will also be 10. And then it's going to go letter, 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 letter. So 26 times 26. Each of these is like its own event. And so we have that problem, and then now we can, just do that calculation to figure out how many different ways that we could create this license plate. Times 10, times, for the sake of being smart, I'm going to type in 26. Whoop, does it say there's going to be 3 letters or 4 letters at the end? 3, so we got to get rid of that. Too many. 26 in the third. So the number of ways, given this scenario, that we could write license plates would be 4, 5, 6, 9, 7, 6, 0, 0. That's a lot, right? 45,697,600 ways to write that license plate. Now I can make a new problem that's very similar that says that assume that the letters, digits cannot be repeated. So in that case, we'd still have 26 letters at the very start to choose from, and we'd still have 10 digits at the very start. But once we've chosen a digit, because we can't repeat this one, we only have 9 choices, because whichever one here has already been decided, we have 9 choices left. And that same idea is going to hold. We want to pick a letter, but one letter has already been selected, so there's only 25 different possibilities, and then 24 different possibilities after that, because 2 of them have been decided, then 23 after that. So this problem would look like 26 times 10 times 9 times 25 times 24 times 23. And of course, there's going to be less here because we can't repeat them. We just have less different possibilities. So there's actually 3, 2, 2, 9, 2, 1, 2, 3. 32 million in this case, 32,292,000 ways that we could write license plates if the letters and numbers could not be repeated. So I could make infinite number of problems this same way by just kind of changing the scenario, but that should give you a good idea how to do license plate problems. And then let's look at some more examples here. We still haven't done any permutation or factorial. Mr. Nyquist is in charge of a mathlete race where the students run a mile and then solve a math problem. Sounds very exciting. I'm sure you guys would sign up. How many ways can his class of 10 finish? So I have 10 students. How many ways can all 10 finish? You guys have to decide if this is a permutation or a factorial problem. It's certainly not a fundamental accounting principle problem because we're ordering a list of objects. So fundamental accounting principle would be like, hey, this object can occur in this many ways, and this object can occur in that many ways. How many ways can they both occur together? That's definitely not what we have here. And then, assuming that we don't have any identical twins that we couldn't differentiate for some reason, we can differentiate between who's finishing our races. So this is going to be either a permutation or a factorial problem. Because we want to know how many ways all 10 of the classmates can finish, we can actually solve this problem just by using factorial. It'll just be 10 factorial. We have 10 objects. In this case, it's people. We want to organize all 10 of those objects. So that would be permutations. But I could change this problem a little bit and easily write a permutation problem instead of a factorial problem. So in this scenario of the mathlete race, first prize is going to be $1,000, second prize is going to be $500, and third prize is going to be $100. 4th through 10 is all just going to be losers. Okay, 4th through 10, we're not differentiating between them, and so this now becomes a permutation problem. We have 10 objects, and we want to select 3 of them. 10 permutations 3. So the difference was with factorial, I had 10 objects, I was selecting all 10. With permutations, I have 10 objects, and I'm only going to select 3 of them. So 10 math permutation 3 would tell me that there are 720 different ways that a top 3 could finish in this race of 10 students mathlete race. So you can kind of see the difference, hopefully, between permutations and factorial. We're actually going to learn another one that's going to even confuse you more, and that is going to be adding a term in the next section called combinations. And you saw probably when we went into math, then we went over to probability, there was P and C. That one would obviously be when you would use combinations. You'd select the third one down, NCR. And the difference between permutations and combinations is that the selected people care what order they're selected in. Obviously, the losers, we know that the order which losers are selected doesn't matter because 4th through 10th all gets the same prize. But order is important for the top 3. Okay, you want to be first more than you want to be third. And so that's this part in which order is important. I just wanted to explain why that line is there. I think it'll make more sense when we start talking about combinations. So that's all I have for you guys as far as section 10.1 goes on fundamental counting principle, on permutations, on distinguishable permutations, and then on factorial. Please let me know if you guys have any questions.